Okay, off we go. So here's where we left off last time. We were talking about, well, I guess, come to think of it, we hadn't really quite started with 7.3. So anyway, first a broad overview. There's a ton of stuff in section 7.3. Each of these theorems really should be its own section, and case could be made that there's so many other things to be said that maybe between the two of them there should be 3 book sections. But again, as Kali likes to do, this is all in a single section for unknown reasons. So anyway, we're going to be basically finding 3-dimensional versions of the theorems that we've been talking about in 2 dimensions. So in a sense. So remember the big one, the first one that we talked about was Green's theorem, right? And there were certain set up kind of points of view that I emphasized really hard on Green's theorem. And remember, I also made the observation that a lot of the theorems that we're talking about in this course are really just the same theorem in a different context. And that's very much the case with Stokes' theorem and Gauss's theorem. They're really just Green's theorem with different details in some sense. So in order to emphasize that, in order to help y'all see that as much as possible, not only am I approaching these theorems in as analogous of an approach as I can take, but I'm also even laying it out on the page deliberately in as analogous way as I possibly can. So I want to encourage y'all to also take an active role in trying to see these analogies and connections and comparisons. When you're studying on your own, look at the process that we're about to do to develop Gauss's theorem, and then look back at the development we did for Green's theorem and kind of do like this and do so we did this. Okay, this is 2-dimensional, this is 3-dimensional. So different, of course, but similar in some very prominent ways. Okay, all of that said, here we go. We're going to have to reevaluate what we mean by the word boundary. Right? The very first thing we did with Green's theorem was to reevaluate what we meant by the word boundary. In particular, boundaries now are to be understood as being oriented things. So here we're looking at a 3-dimensional solid, what I have shaded here, this region called R. 3-dimensional solid, its boundary is a surface, right? But in particular now, we need to understand this as an oriented surface, and oriented according to a particular convention. And here's the convention. The convention is away from the solid. So now, for example, if you're looking at a point right here, I claim that is away from the solid in the sense that the solid is this business over here. Toward the solid would be like this, into where the solid is, right? After all, the boundary is kind of the border between where is solid and where is not solid, right? So toward the solid would be like that. Away from the solid is like that. Now, commonly, this is misunderstood as outward. And I think it's a dangerous phrasing to call it outward, because while in this case, look at this point, yeah, sure, it looks outward. Right, fine, right? But if you look at this point down here, that is the direction that is away from the solid. Again, the solid being, what I have shaded down here. So away from the solid like that. And I don't think really outward communicates the right thing here. I feel like that plenty of people would call this inward. Does that make sense? So again, be careful about this. Kind of analogous to when we were doing Green's theorem, and I pointed out that the sloppy way to say it is counterclockwise, but it isn't always counterclockwise, right? There was this other more careful phrasing that you have to follow. So anyway, same, analogous, different, of course, geometrically different, but analogous with the story there. Okay. All righty, moving along. As with Green's theorem, we're going to understand Gauss's theorem as concerning an accumulating quantity, and the accumulating quantity is boundary flux. Excuse me. So boundary flux is what we're going to associate to any given solid. And I claim that boundary flux accumulates, and let me add in the phrase here, accumulates over solids. That is, if you have a solid and you're interested in its boundary flux, you cut that solid into pieces and you look at the boundary flux of the one piece of solid and the boundary flux of the other piece of solid. That's the solid is the whole that we're going to be thinking in terms of how it relates to its parts. Okay, so accumulates over solids. Okay, so now how do I know that this works? How do I know that boundary flux, in fact, accumulates over solids? Well, let me just kind of cut to the punchline. When you cut this solid into these two pieces, R1 and R2, here's your new face that you're creating. That's your shared face, right? That shared face is going to show up in the boundary of the boundary flux for R1 and in the boundary flux for R2 as part of the boundary of R1. Away from the solid is that direction to the right, right? But as part of the boundary of R2, away from the solid is that direction, namely what you'd call here to the left, right? So this shared face, it appears twice, but with opposite orientations, and so they cancel. Now again, it's geometrically different than what we saw with Green's theorem. With Green's theorem, there was an area, and we were talking about circulation around, not flux through. The boundary was a curve, not a surface. All granted, yeah, totally different geometric scenarios, but check out how similar, kind of analogous, right? New piece, opposite orientations cancel. That's exactly the same. Okay. All right, so nice comparison to be made there. Please do compare and contrast. Take a look. Okay, we've made this pitch a bunch of times. I'm going to kind of go a little bit more quickly through it here because it's morally the same point. Roughly speaking, when you have an accumulating quantity, you can think of that quantity as being a kind of a stuff. And it seems like a weird thing to say when you're thinking about boundary flux, kind of like it was a weird thing to say when you were talking about boundary circulation, because boundary flux, it's got the word boundary right there. And we tend to think of it, therefore, as being something that happens on the boundary, like it says. Okay? But, importantly, if you just kind of forget about the word boundary just for a moment, just think of it, look, we have a quantity that's associated to solids. I think it's a pretty easy pitch that quantity that you associate to this solid is something that you can think of as developing or originating, or however you want to say it, in the solid. And if that's the case, if we think of this quantity as distributed over the interior, what we would need in order for that to make sense would be that if I were to chop it up, that quantity, that the whole would be the sum of the parts, which it is, right? We've already established that this is an accumulating quantity. So whether it is, physically a stuff that is actually inside of the interior isn't the point. It behaves like it is, so we can pretend that it is. And everything's going to make a lot more sense if you take that point of view. So now just a quick reminder, and I know y'all already remember this and you've heard me talk about this at great length, but the most persuasive at this point, I think, most persuasive example that I have of something computed on the boundary that's actually happening in the interior, let's think back to change. Right? We can think of the fundamental theorem of calculus ultimately as being about an accumulating quantity called change, f of b minus f of a. It's computed by looking at a and b, which of course is the boundary of our interval. Is that where change happens? No, of course not. You can see, look, here it is. This is where the change is happening. I can see it. Check it out. Look at the function change. There it's changing, right there. So these, in the interior of the interval, is where the change happens. You measure it at the boundary, but that's not where it is. That's not where it's happening. That's not where it comes from. That's just where you measure it. It's happening in the interior, and I strongly encourage that y'all try to think about boundary flux in that same way. And again, geometrically, it's different. Geometrically, it's harder to kind of see it in that sense. We don't have enough dimensions to be able to draw the graph, for example, of a three-dimensional vector field. That'd be six-dimensional. Out of the question to visualize it. But just view it this way, and everything will just make much more sense. Okay, and by the way, I do have a really good physical metaphor coming up that will help understand this idea of measured on the boundary but happening in the interior. Okay, when you have stuff, you can talk about the associated density. So mass, right? If you think about mass per unit volume, well, mass per unit volume is what you multiply by volume to get mass. And we call this a density, this mass per unit volume, because it's fits into this kind of general category of stuff per unit size, right? Accumulating quantity appropriate to the application per unit size appropriate to however that quantity is distributed. Okay? So ripping off the same idea. Flux, that is boundary flux, as we've just discussed, is a quantity that has the feature of accumulation. We can view it as a stuff, just like mass is a kind of a stuff. So we can talk about the amount of flux per unit volume. This thing, flux per unit volume, is what you multiply by volume to get flux. And in that sense, this thing, flux per unit volume, also can be thought of as a density. So this is what we mean when we say the word flux density. By the way, very, very common term. A case could be made that some of the other densities that I've pitched to y'all, like change in density, it is possible I might have made that up. I'm not sure. I have not seen it that I recall anywhere else. So not a popular term. Circulation density is out there. I did not make that up, but it's not super common. But this term, flux density, is extremely common. In my physics major, y'all are largely engineers. Y'all are probably going to have similar experience. In my physics major, I heard the term flux density a bazillion times, more than any other term that I could associate with this construction or this idea of flux per unit volume. So extremely common term, not something I've made up at all. You're gonna hear, this is in your future. You will hear the term flux density, and this is why they call it that. Okay. All right. Now that said, other things to say about flux density. We have a formula for computing it. Here it is. That thing right there. Nice handy-dandy little formula. Notice it's computed out of the coordinates of the vector field. Right? Whatever vector field we're talking about, it has coordinates PQR. Here's your formula for flux density. By the way, you may recognize that formula. We saw exactly this formula back in Chapter 3. In Chapter 3, we were calling it divergence. Right? Well, that's what divergence is. And we didn't really, we didn't have the context for me to be able to make sense out of saying divergence is flux density at the time, because we had just barely started talking about flux, but we hadn't talked about boundaries. We hadn't talked about boundary flux for sure, right? We were only considering flat surfaces. We had no possible ability to do so. But that's what divergence is. Divergence is flux density. Along the lines of the term divergence, sometimes this is written as div f. Y'all will recall from Chapter 3, divergence is also sometimes written as del dot f, Really nice notation. Now again, in my physics classes, which are probably more analogous to y'all's future, I saw this notation, del dot, almost exclusively. Right? Barely ever saw in a physics class. So heads up, you're going to see del dot. Make sure when you see del dot vector field, you should read this as divergence of F, and in your mind, when you see del dot, you should think flux per unit volume. Okay, let's see here. So yeah, one last thing before we go on, and that is let's think about, what does this help us understand about divergence then? And you may recall that in Chapter 3, I kind of punted and said, well, it's going to turn out, nebulous statements about the future of, what we're eventually going to be able to talk about. And the claim I made, as I recall, was that, it's kind of a measure of to what extent the vector field is kind of emanating outward in some sense, to what extent the fluid is kind of in the net at least kind of flowing away from a given point. Right? I think those were some terms that we used. So I couldn't give you any context for that, but now we have it. Why is divergence measuring how much the fluid is flowing outward from a general vicinity? Because divergence is flux density. Flux is literally, keeping in mind when we say flux in this context, we're talking about boundary flux, right? If you have a boundary, some little region like this, boundary of a little ball, flux is literally saying, to what extent is the fluid flowing outward through that boundary surface? So, outward flow through a surface per unit volume. And I think that justifies this point of view that I basically asserted back in Chapter 3. That's measuring how much the fluid is kind of emanating outward away from a given point. Same image. Okay. Now let's see an example. Here we go. We have a vector field. This vector field through a surface, ball of radius 6, will generate a certain amount of flux. I suppose you could even compute that amount of flux. We don't need to compute that amount of flux for this example, but you could. So given that vector field, given that there is a certain amount of flux that's being generated here, where is that flux coming from? And of course, it's not coming from the boundary of the solid that we're measuring it on. It comes from the interior. Of course it does. That's where accumulating quantities happen. They happen in the interior. So, is more of it coming from this point, or is more of it coming from this point? Both of these points are in that interior. Where is more of this boundary flux coming from? So now, for analogy purposes, recall back to the single variable fundamental theorem of calculus. Recall this example, right? Silly, obvious example of, where is the change happening? You look at the picture, right? You can just see how the function is changing, and you can see it's changing faster. Over here on the right, it's changing slower. Over here on the left, most of the change is happening for these larger values of x. You can see it right in the picture. But algebraically, the way we're going to come at that, you want to know where the change is happening? Change density tells you where the change is happening. Change density being the derivative. You compute the derivative. You plug in your 2 points, right? The 1 and the 2 where, we want to compare. You plug those in. And you want to know where more of the flux is coming from? Okay, fine. Look to see where the change density is more. And the change density is more at 2 than it is at 1. Totally analogously, you want to know where the flux is coming from? Where is the flux created? We'll look at flux density, divergence. Make sure you can do this, by the way. Make sure that you can take this vector field, compute its divergence. Remember, it's computed with certain partial derivatives, formula on the previous page. Make sure you're computationally good to go on that. So flux density tells us where the flux is coming from. And plugging in to that, plugging in our 2 points, our 2 interior points, A and B, and okay, you want to know where more of the flux is coming from? All right, more of the flux is coming from where the divergence is bigger. So B, apparently. Sort of half again more, a little over half again more. Is that cool? Okay. So a quick little digression to talk about interpreting divergence, and but now we're going to go back to developing this theorem. We have all the tools that we need. We're ready to put the pieces together. And reminder: we started off with this idea that we're going to think of boundary flux. Notice boundary, right? Vector surface integral. So this is flux, right? But specifically through a boundary. You can think of this as being an expression or a formula, but I want to think of it as quantity. The first big observation that we made is that quantity accumulates. The whole is the sum of the parts. That's what I have here. Whole is the sum of the parts. And then furthermore, with the understanding that this is a kind of a stuff, and you can talk about stuff per unit volume. Namely, we can talk about the associated density, which we've already discussed as divergence. So now, again, if you go back to chapter 6, and if you look at how we developed Green's theorem, lots of differences. This is 3-dimensional. Green's was 2. This is about flux. That was about circulation. The density was a different formula because it's a different kind of a stuff per unit, a different kind of size. A lot of differences, but it had the same general feature of we took some quantity, we observed that it accumulates, we noted the associated density, and declared a theorem. And that's exactly what we're doing here. So very, very strong analogy. Again, I encourage you to dwell on those connections. So anyway, here's our final punchline. A boundary flux can be computed with a triple integral of divergence. That's Gauss's divergence theorem. How we doing? Everybody all right? Okay. All right, let's see an example. Now, this is a computational example. Let's see, I'm going to try to get this all on the page. There we go. About like, oh, you know what? I can hit that button. Okay, that's better. There we go. So, yeah, this example, we're going to compute a flux. It says so right here. We want to compute a flux. Our new theorem concerns a flux. Right? So we're optimistic. We're hopeful that I can just take the flux question I've been asked, use Gauss's divergence theorem, and compute. Here's the problem. A nasty little detail. Very, very important. Gauss's divergence theorem, as we've said several times here, is not about just any old flux you want. Gauss's divergence theorem specifically only applies to boundaries. Right? This is really important. Oh my gosh, so important. It has to be a boundary. Now, there's a couple of points to make related to that. Why does it have to be a boundary? Well, look at the development that we argued. Right? We made this accumulation argument, sort of a cancellation argument, and that only works because we were talking about boundaries, strictly oriented the way that we indicated. Right? So the fact that it's a boundary is where this all came from in the first place. But even more sort of like bluntly, just visibly obvious right here in the formula. This has to be a boundary because the thing it's a boundary of is our domain for our new triple integral. So if you look at a flux where the surface is not a boundary, then there is no solid that it is the boundary of, meaning there is no solid to even talk about doing a triple integral over. Right? So what's going on here, it's not that, this is a fine detail and, these two integrals are just different if it's not a boundary. No, it is that there is no triple integral to even talk about this flux possibly equaling. The whole thing doesn't make any sense at all if it's not a boundary. Does that make sense to everybody? Okay. Really important point. Please do be very, very careful. Only attempt to apply the divergence theorem when the surface whose flux you're interested in is a boundary. So we better pay careful attention to that. Let's think about our surface down here. Our surface down here. We have the inward-oriented unit sphere, and here, let me do it like this. There's the sphere, inward-oriented. That's what our S is. And is this, as I have it drawn here, this S, oriented inward, as indicated here, is that a boundary? And tragically, no. It does not. Right? Again, very, very important detail doubles. Boundaries are oriented away from the solid. Loosely speaking, oriented outward. Right? And that's just not what we're looking at here. Oops. Do it like that. So, we lose. Everybody see? Everybody happy with that? Okay. All right, here's the good news. Here's what I can recover. While the surface oriented inward is what I'm actually interested in, I can easily talk about the opposite orientation, namely just orienting it outward. Y'all remember this notational thing. If you just put a superscript with a minus, that represents same underlying surface but with the opposite orientation. Now let's just for while we're here, let's think about this orange surface, the outward-oriented unit. Outward-oriented unit sphere. Is that a boundary? Well, sure it is. Of course it is. It's a boundary of this ball that I have in gray right there. So we can apply, right? We can apply Gauss's divergence theorem to this orange outward-oriented S minus surface. We cannot apply it to the surface we're interested in. Okay, so fine, no worries though. This is still something we can totally work with, and in particular, again, we're interested in that blue integral. Well, the difference between the blue integral and the orange integral through this orange S minus surface, the only difference is that S minus is oriented the opposite way, and therefore we get the negative value of that flux. So I've very conveniently connected the flux that I want to a flux that I know how to compute, namely a flux to which Gauss's theorem applies. How we doing? Everybody with me? Questions? Okay. I know it's a Friday afternoon in a hot room and everybody just wants to nap. I kind of want to nap as well. But anyway, feel free if you have any questions, let me have it. Okay. All right. Okay, so let's finish this up. So the big idea, of course, here is that S minus is, in fact, that boundary. And once you have it as a boundary, now I can invoke the divergence theorem. Gauss's divergence theorem says that boundary flux is this triple integral of divergence, and now it's we're off to the races. We've negotiated the question into a form that we can plug into the divergence theorem. Okay, now there is one cool little trick that I think we need to talk about just to make sure. You compute the divergence, no problem. Divergence is 3 plus x. Make sure you can do that. Right? Make sure you see where this 3 plus x comes from. Here's our vector field formula, x partial of this, y partial of that, z partial of that. So 3 plus x. And now how are we going to compute this integral? And that integral, let's see here, my domain is a ball. My first instinct is to think spherical coordinates. And you could totally do that. you could totally crank this out in spherical coordinates. Lots of trig, but it would work. It's not even all that bad, I suppose. Okay. Here's the much better idea, though. Much better idea is to notice that you're welcome to break up an integral with two terms in it into two separate integrals. And the beautiful thing about this is that even though our original integrand here is not constant and it's not symmetric, it has no nice properties that we can capitalize on. Yeah, but the 3 part is a constant. That's easy to work with, right? And the x part is symmetric. And you can make a symmetry argument on that part. So this happens to be, and this happens a lot. Again, another thing, personal experience, y'all are going to get a lot of use out of this. When you're looking at nasty integrals, if there's more than one term, entertain the possibility of breaking it up into multiple terms. Effort is not, let's see how to say, effort is not an accumulating quantity, right? The effort of the whole is sometimes way more than the sum of the efforts of the parts, if you allow me to stretch a concept there. Is that cool? Everybody? Oh yeah, question.
Is x minus just arbitrarily that boundary? Like, is that just given in the
problem? No, it's not arbitrary. It's that's just how boundaries work. So if you were to think about B as this solid here. So this solid ball, right? And if you ask, well, what is the boundary of that solid? Well, boundary means kind of the border with the understanding that it's oriented away from the solid. And it just happens to be that that boundary is exactly the opposite of what we were asked. We were asked for, coincidentally, the same sphere, just, oriented inward. And so it's just a kind of a lucky break. Yeah. Does that make sense?
Yeah.
Okay. Yeah. Yeah. Okay. All right. So let's talk a little bit about some physical examples. We live in a three-dimensional world. This is a three-dimensional theorem. Probably expect there to be some nice applications. Turns out there's lots of powerful applications, really important, powerful applications. And I like to think of some of these, by the way, not so much as applications, but as manifestations of the theorem. Right? So the idea is a manifestation. By what I mean by a manifestation is the physical world, the way the physical world is put together in some ways is itself the perfect illustration of what the divergence theorem is saying. And my favorite first example of this is a light bulb. So I'm going to imagine we have an LED light bulb. LED light bulbs are teeny tiny, right? I don't mean the big whole plastic or glass dome part. I'm talking about just the LED itself, right? Teeny tiny little thing. And so it's approximately, not quite, but approximately a point. It's bigger, right? It's finite size. What it does is it shoots out photons, right? That's what light bulbs do. All these light bulbs are just throwing photons all over the place. And so you get this outward flow of photons. Now you'll notice the way I have this drawn that the field vectors get shorter as you move further out. Now what's going on there? Are the photons slowing down? Not at all. Remember, sometimes when you represent the flow of a fluid, sometimes you represent that fluid flow with velocity, but sometimes you represent the flow of fluid with density times velocity, right? And that's what I'm doing here. Density times velocity. For example, when you use density times velocity, that means flux will give you quantity of fluid per unit time as opposed to volume of fluid per unit time. And so if you're interested in quantities, you got to multiply the velocity times the density. So that's what I'm doing here, and appeal to your sense of how this works, that this LED is shooting out photons, but when they're first shot out, they're all kind of close together, and so there's a high photon density near the LED. But as those photons get farther and farther away from the center, they also get farther and farther away from each other. And so the density goes down. And so even though the velocity of photons is constant, density times velocity is not constant, right? And so that's why the field vectors get shorter as you go further out. Yep.
So the photon density doesn't change over time?
It doesn't change over time. Yeah, it does change over location. Yeah. So what I mean by not changing over time is that when we have light bulbs, I mean we're generating photons as we speak, right? There's photons just shooting out of there. If I were to hold my hands like this, I'm not collecting photons, right? They come in and they bounce out, or they come in and they pass through. 15 seconds later, different photons are coming in and shooting out, but they don't collect. That's all. Does that make sense?
Yeah.
Okay, so there's our vector field. Now here's what I want to ask about this vector field. Let's see, let me get rid of all of the stuff. Actually, let me leave that part there. Let's ask about the flux through this sphere. And what can we say about the flux through that sphere? Well, the bulb is shooting out photons. Every photon that gets shot out of that bulb is going to have to pass through that sphere. So however many photons per unit time this is creating, that's how many photons per unit time are going to pass through that surface. So quantity per unit time of photons through the surface, however many photons per unit time are being created, that's how many are passing through the surface per unit time. So we're going to have a significant flux. However much light's being created, that's the flux. Okay. Where is that flux coming from? Where is that flux happening? What's the origin of the flux? And now let me make a silly observation. Wrong color again. Let's see here. Let's talk about this green point right here. Is there any flux? This purple flux that we've measured, is it coming from this green point? No, of course not. There are photons that go through that green point, but they go in and then go right back out. Nothing's being created there, right? And likewise, if I were to look at a point on the surface, on this purple surface, there's nothing being created here either, right? Photons go in and then go out. Any photon that goes out just got through coming in. Well, that's not where the flux. That's where we measure the flux, right? But where is the flux actually coming from? Well, I think it's an easy pitch that the flux is coming from where the light bulb is. That's where the flux is coming from. That's where the flux is created, because that's where the photons are coming out of. Right? Does that make sense to everybody? You measure a certain number of photons per unit time passing through the surface. All of them came from here. Right? So now I claim divergence is what's going to measure this for us. Divergence is what's going to point directly to where the flux is coming from. And if you were to measure at points like this, and in fact any point anywhere in or out of that region, just don't get too close to the bulb itself, right? But anywhere else, all this whole green area, there's no photons originating in anywhere in that green area. And if you were to measure the divergence of the vector field there, you would get 0. So the divergence is doing its job. No photons are coming out of that point. Divergence will be 0 at that point. On the other hand, where are the photons actually coming from? Well, they're coming from where the bulb is, and at that point, the divergence will be huge. Right? Very large divergence at that point, pointing directly that that's where the flux is coming. Yeah, sure, you measure the flux on the boundary, whatever. You pick this sphere arbitrarily, right? There's nothing actually originating there. It's coming from the bulb itself. And divergence tells us. How we doing? Everybody with me? Okay. So again, what I like about this, two things I really like about this example. One is it's about a light bulb, right? It's totally relatable. We all understand light bulbs. We understand it's believable that light comes in little particles that fly along. I think that's all pretty believable. So there's nothing creepy or sophisticated or invisible or hard to relate to about a light bulb, right? So it's very relatable in that sense. And I also really like how this makes a relatably, believably physical example of flux being measured on the boundary, but literally coming from the interior, right? And it's a hard pitch. When I phrase it like this right here, it seems so sort of creepy and unnatural and forced and arbitrary and manufactured and unsatisfying. Not here, right? Yeah, light's coming from the light bulb. Pretty believable. So please give this some thought. Spend some time kind of chewing on this metaphor, right, and trying to relate that to the suggestion claim that I'm making here. Well, I think there's a lot of benefit to be gained there. Okay, let's do another example, another physical example. This next physical example is about a different kind of a fluid. Not just a different substance, but a qualitatively different kind of a fluid. So here we're going to talk about a gas. And in particular, I don't really care what kind of gas it is, whatever, helium, hydrogen, who cares? But we're going to imagine there being a finite amount of gas. I like to think of this as happening out in outer space somewhere, right, way far away. And there's just a gas cloud, let's say, out there about so big, right? And that gas takes up a certain amount of space, certain quantity of gas, certain volume that it takes up. You can talk about the density of the gas, right? What would happen if we, for whatever reason, the temperature started to increase? And I don't know if y'all have had gas law physics classes, but if you have a gas and the temperature goes up, well, then the volume will increase, right? So the gas will start to expand outward. Does that make sense? Does everybody believe that? Okay. All right. So that's a flow of a fluid, right? There's a gas as a kind of a fluid, and it's kind of flowing outward. So real quick, I claim that the flow will be, well, of course, being outward, it's going to be like that, away from the center of the cloud. Right? Outward in sort of all directions. The gas right at the center of the cloud, now again, physical hand-waving appeal, if this is my cloud of gas, and if it starts to expand, yeah, the gas on the edge is going outward, and the gas on this edge is going outward. But if it's expanding symmetrically, the gas in the middle isn't going to move at all. It was in the middle, it stays in the middle, because it's expanding in some sense, and it's being pulled in some sense in both directions. So the actual flow then it's not a constant speed of flow outward. It's flowing less quickly the closer you are in to the center, and more quickly the further you are out. And so this is why I call this this flow. I claim that the formula is something like this. It's some multiple, who knows, times the position vector x. So outward, and the further you are out, the faster it's going. What do you think? Everybody buy that? Kind of plausible? Okay. All right. Okay, so now with that noted, again, let's think about a flux. Got ahead of myself. Sorry, one last thing to observe. So we have a certain amount of gas. It's taken up a certain amount of volume, so it has a certain density. As it expands, it's still the same amount of gas, right? We're not generating new gas. It's still only so many particles of gas. That gas is taking up more volume, though. And so as such, because it's taking up more volume, the density is decreasing. Right? Quantity per unit volume. If the quantity is the same and the volume is going up, density is going down. Okay. All right. Okay, so now, all that established, let's think about the flux. Again, I'm going to pick a nice sphere here arbitrarily. And in that sphere, there's gas flowing outward. Right? So, of course, there's going to be a flux. There's going to be a significant flux through this sphere. Gas is leaving that sphere. Right? So, altogether, then what does that flux represent? Well, there's a certain amount of mass in there to begin with, and as the gas flows out of this sphere, there is less remaining gas in the sphere. Right? So flux, what that flux is measuring is quantity of fluid that is leaving our solid. All right, now let's write down the divergence theorem, try to figure out what this means. There's the divergence theorem. We can totally compute the divergence. The divergence is 3K. By the way, this is a little computational exercise. Make sure that you can look at the formula for divergence, compute 3K from this vector field. It's a little bit weird at a first glance. The thing that's weird is this vector field is written in a vector form. All you got to do is write this out in coordinates. So this is kx, comma, ky, comma, kz. And you write it out in coordinates. You punch it up with the formula we already have for divergence, and that will give you 3k. Okay. All right. So that noted. What does this 3k tell me physically? And remember, it's divergence, and divergence is flux per unit volume. And now let's just think this through. The flux is quantity per unit time leaving our solid. Quantity per unit time leaving. Divergence is that per unit volume. Okay, so quantity per unit time per unit volume. Okay, quantity per unit time per unit volume. Let me say that again, but I'm going to kind of move the words around a little bit. Instead of thinking of it as quantity per unit time per unit volume, think of it as quantity per unit volume per unit time. Quantity per unit volume is density. So in this case, because we're talking about given all the particulars, this divergence is representing the rate that our gas density is decreasing anywhere you might be happen to be looking. So at this point right there, as the gas expands, what this 3K is representing is, all right, how fast is the density going down there? And at this point over here, 3K represents, well, how fast is the density going down there? Now you're going to notice that divergence is constant. That means that the density is decreasing at a constant rate. And, well, yeah, it better be, because as the gas expands, of course, the density remains uniform, as it goes through. So it has to decrease at the same rate at all points. So anyway, different interpretation of divergence, because this is a fundamentally different kind of a fluid. And always make sure to think about what kind of a fluid it is and how your fluid behaves when you're making these interpretations. So real quick, and then we'll call it a day. Oh, am I? Yeah, real quick. The big difference between these fluids, the light bulb is literally creating photons. We're not creating gases, right? We're not creating more gas. This flow does not represent the creation of gas. This flow represents the creation of photons. So that's a fundamentally different kind of a fluid. It's not about what the particles are. It's about where this fluid is and what rules it has to follow, right? So that's the big difference. We'll draw the line right here and pick up with more of this later on Monday. Y'all have a good one. Have a great weekend. And don't forget about tenants if I didn't already get you.